So yeah, welcome everyone to this final presentation for this year's GLA Summit. My name is Anton Sundqvist, and I'm going to present on the topic of unit testing. And the main topic is going to be LUnit, which is a new open source tool for unit testing in LabVIEW. I wanted to start by giving a brief introduction to myself for those who don't know me. I'm a Finn, but I currently live in Stockholm. I moved here after finishing my studies in Finland to start working at NI, actually, at NI Stockholm. Since that, I have been also working at Novato Solutions, which is a Gold Alliance partner and NI Center of Excellence here in Stockholm. But currently you can't probably see it, but there's a lot of boxes here. And the reason is that we are actually moving back to Finland now on Saturday, actually. So we are just packing down our whole life into small boxes here to ship them over. So once I get to Finland, my aim is to start up my own LabVIEW consultancy business. So the presentation was very interesting yesterday about driving an NI-based business, or the panel discussion that we had. Also, if there are people from the Finnish LabVIEW community present, I'd be more than happy to get in touch. So please reach out and we can catch up at some point, hopefully. About myself, I'm passionate about software design, and the idea of software craftsmanship or software as a craft really resonates with me. I'm also the author of LUnit, which is the topic of this presentation. And I've done some LabVIEW and TestStand in the past. So to start off this presentation, I want to highlight a very talented woman who is called Linda Rising. She's an American author and speaker, and she has played a major role in driving adoption of software patterns in the industry, which is something that I'm myself very interested in as a topic. She was also on episode 238 of Software Engineering Radio, talking about a topic called the Agile Brain, which, despite the catchphrase, is actually a very interesting and insightful discussion. So here would be a good tip for your commute to work, to have a listen to this discussion or conversation with Linda on learning and how we treat that in organizations and related to software development. Cool. So I just want to briefly go over the agenda before we jump into the presentation. I want to start by talking a bit about the context, really, within which the tools like LUnit is often used or bring the most value. And I'm going to discuss the topic of test-driven development a bit, not in depth, but still. Then I'm going to briefly touch on the state of the world when it comes to unit testing in LabVIEW. And then we're going to get on with looking at LUnit and what that can do for you. And we're also going to look at how we can leverage this tool to test larger hierarchies of classes, which is actually one of the pains which I felt, which led me to start this project, really. Continuous integration has been in a lot of the presentations during the past 24 hours, and I also want to touch upon how we can integrate the running of the unit tests into a CI system. I'm also going to discuss a bit about the performance, why it is important, in which way, and how LUnit performs in comparison to other tools out there. But before we look at the topic, I just want to give some acknowledgements where they are due. I want to start by recognizing the JKI VI tester, which has thus far been my weapon of choice when it comes to unit testing. I think for what it is, it's a very good tool, and it's been direct inspiration for this tool. So if you have used VI Tester before, you will be very familiar navigating and using LUnit as well. Maybe a bit with the glimten ögat, as you say in Swedish, with a bit of humor. COVID-19 actually was the thing that kicked off this project, because I suddenly found myself with a lot of time on my hands and desperately needed a side project. And at the same time, LabVIEW Community Edition was released. So these two factors made me pick up this as a side project, which has been cooking now for a while. And I'm excited to share with you what I've been working on. So why do we test our test code? This is a good question, and it's an interesting discussion to have. I mean, if we start testing our test code, is there no end to it? Are we going into an infinite loop where we just test the test code, which tests the test code? And of course not. We are. It doesn't really make sense. It's just silly. But my point being that testing the test code is something that's it maybe gets overlooked a bit, and even if the code that goes into the products we are testing are probably tested in many different ways, we might be a bit not that diligent about testing our own code, which we actually develop. I think everyone tests the code in a way or another. I think this is probably the worst way you can test your code, to test it in production. If you're a professional software developer, you probably want to know that your code works before you ship it to production or deploy it in some kind of way into the real world. There's also these kind of situations where it feels like the code is so entangled that when we fix a bug, we just cause more of them and they kind of multiply. This, I think, is a symptom of course, bad design. We have code which is tightly coupled, but also it's a symptom of the lack of test coverage. Because if we had proper test coverage, we could just run the automated tests, and they would probably catch the new bugs which appear, and we would be able to patch up the bug. And the reason I think this is dangerous is because as time goes, if you're afraid to change the code, if you are afraid of creating new bugs when you try to fix something, then the code will rot very fast, and it will just degrade over time, and it will become unmaintainable pretty quickly. So this is a bit of the rationale why you might want to test your test code or your LabVIEW code. So what can we do about it? If we look elsewhere, there's many different strategies or paradigms to do testing. I think this is on a high level what applies the best to the kind of projects I'm familiar with in LabVIEW. We have some kind of pyramid where we on the top have what's called acceptance tests. And these are the tests which the customer or the user of the software cares about. It might be just a straight Excel document with a lot of rows with small tests which you check off together with the customer to accept the delivery or to prove that the software confirms to the specifications you have gotten from the customer. So these are very expensive, very slow to run, and it takes a lot of time and money to actually run this. So that's not something that you would like to do every time you have added a small feature to your code base, and of course you shouldn't. For that we have what we call unit tests, and these are basically on the lowest level then, small tests which test a very specific part of the code at a time. And the idea is that we test that part of the code in isolation, so that if there's an error in the code, we can quickly find it, patch it up, and fix it. And we don't need to debug the whole application end to end and go deep in and hunting the bug down. We can just focus on a very specific behavior that we try to fix. And then in between, we have what's called integration tests. So if unit tests are tests in isolation, when we then want to know if more than one unit works together, then we test them together in some kind of way. And that's what we call integration tests. And the line is a bit blurry, to be honest, at least for me. And you can use the same kind of tools for integration tests as you do for unit tests. But let's talk a bit more about unit testing and what a unit test is. So to give some kind of definition, this is my own definition. It's not from a book or anything academic, but a unit test is simply a small piece of code which exercises the production code to get some kind of results, to basically see that it's working as expected. As I mentioned on the previous slide, we try to test the code in isolation as far as possible. And the reason is that if you test it in isolation, it will fail in a very specific way, and it will be very easy to fix that specific thing. If you test a lot of things simultaneously, or if the tests are run, well, in more of an integration test style, then the fail could depend on a number of different reasons. So we want this broad base of tests to be very specific and low level, or yeah, at least specific, which is then the next point. Each test should focus on specific behavior. And it's pretty common to have this kind of a paradigm that you have some kind of preconditions. Given something, when something happens, then we expect this to happen. And the then is really what is the test part, where we assert that something happened and check that it really passes the test to report the results in some kind of way. And in my opinion, a unit test should be very, very expressive. This is the most important, let's say, feature or property of a unit test, is that it should be telling us what is the unit test actually doing at a glance. So if you just open it up, you should be able to tell this is what this unit test does, and if it fails, then you will intuitively know what has actually failed. But that's a bit beyond the scope of this specific presentation. I already mentioned this topic of test-driven development, and this is something that was popularized in the late 90s, early 2000s by the extreme programming community and the people there. And even if extreme programming at the time was rather extreme, today I would say it's quite mainstream, at least if you look outside of the LabVIEW world, and it's not something that's considered extreme in any way anymore. And especially test-driven development, this is something that's proven to work. And for me myself, it's been a bit like seeing the Matrix when I first tried using it. It's very powerful technique. So just to give a brief overview of what it means. So the idea is that when you develop a piece of code, you would first start writing a test for the production code. I wouldn't be too dogmatic here and say that you must write the test code before the production code. But the important thing is that you write the test at least at the same time as you write the production code, so that you don't apply the tests afterwards. And this is important because it will ensure that you write the code in a way which is testable. And this brings a lot of other benefits with it, which I'll come to in a bit. So you have written your test, then you run the test, and you see the test fail. This is really a sanity check to see that the test that you have run, that you have just created, it actually tests something useful, it actually fails. If it would always pass, then you could just delete it. It wouldn't really add much value anyway. What you do next is you implement the feature. So you do it as quickly as you can. You shouldn't care too much about how the wires are drawn, if they are straight or not. You can come back later and clean that up. But you just try to fix what is, you have some kind of idea of how you want to solve this feature. You implement it and you test it, you see the test pass. So by doing this, you can quickly just factor out solutions which would not work or which are just plain bad, and you can find solutions which work. And then when you get the test green, you should also run all the other tests which you have written previously. And in this way, you can ensure that you haven't broken something that you built before. And when everything is green, when you know that everything works, then it's safe to refactor the code and rewrite it, extract classes, methods, apply patterns, whatever, to make the code better in some quality sense or code quality measure. So we have this kind of loop where we have red, green, refactor. This is typically what the test-driven development community talk about. You have the red failing test, you make it pass, and then you refactor. And if you do this well, you should be doing it very quickly, because you want to focus on a piece at a time, a detail at a time, and not have everything write everything at once. So you want to have this loop as quick as possible, short feedback loop as possible. And typically you can reach cycle times on the order of minutes. So a few minutes to write a new test, implement a feature, and see it pass, and so on. And because we have such short cycle times, it's very important then that when we run the tests would not be interrupting the workflow. They should be just immediately checking your code, and it can take a long time because then you get distracted and you will lose your workflow basically. So I already mentioned that I really like this kind of way of working, and I'll try to explain why I like it a bit before we go into how this applies to LabVIEW. So by using this kind of methodology, we can actually prove that the code works. And a common misperception here might be that we are proving to the stakeholders that it works or something like that, but that's not the case. The point is that we prove to ourselves as the developers or to our team that the code which we have written actually works as we says it will, as the test says it will. And we simultaneously know that we haven't broken anything that anyone else implemented earlier, because all the other tests should always be green. You shouldn't implement something that breaks an existing test. So this is really, really, really important, because now we know that what we have written, at least for any kind of case we have been able to come up with, it works. So when we ship this to the customer, we know that it worked. It didn't even only work on my machine, it worked with the tests that we have written. And we can run it in a CI environment to make sure that it runs on a clean machine and not on a development computer. So this is very important, and it gives you a lot of confidence, and you can actually sleep better at night. So I think this is, for me at least, maybe the biggest benefit of having tests to the code. It might be obvious to some, but still, I wanted to highlight it. We also, as we know that the tests will test the code, we have the courage to rewrite and refactor, because if we break something, we will know it immediately. We will know it directly. As soon as we have made a breaking change, our test will turn red, and we will know that we need to fix something up. So this lowers the bar significantly to just improve the code over time. This was a bit what Deb talked about with keeping the code base clean and having test coverage in the presentation about NXG or lessons learned from the NXG project. Another important aspect of using this kind of workflow is that it actually directly improves the design. It's not only checking that it works, it actually forces you, it puts a kind of a pressure on your design, because if you want to be able to test it, it needs to be testable. And code which is testable is inherently decoupled. If you have coupled code, it will be very messy to test it. So that's something that you want to avoid. So you get, not, I wouldn't say for free, but you get, as a side effect of using this pattern or this development practice, you will get a very nice design if you do it well. And also the tests provide documentation, and it's not only a written document somewhere which gets outdated. It's actually a piece of code which you can then read and see what it actually does. You can execute it to check that it actually does it. So this is documentation which will never get old, because if it gets old, outdated, then it would fail. As long as it passes, it's correct. The truth is always in the code. And then we have this last point I want to make, is that if you find a bug in the code, you would then create a test which shows the bug. The test is red, you fix the bug. The test turns green, you might do some refactoring while you're there. Be a good Boy Scout, leave it a bit cleaner than what it was when you came. And when you have fixed this bug, you just save the test for later for your regression test suite. And if it reappears at any time, you will know about it. So it's very powerful in that sense as well. So let's have a look at LabVIEW a bit and the tools available. I already mentioned one of them, which is VI Tester. And as I mentioned, I really like this tool for what it is. And it uses the XUnit architecture, which is used widely in the industry, and I'll return to that later as well. A lot of people use Karaya. Karaya takes a more a new view of defining a new method. Let's say Karaya doesn't put as much structure around your test. You can have any VI be a test as long as you just drop the assertions in there. So it's a bit different than the VI tester, which forces you to create the tests in a specific way and organize them in a specific way. But these are very fine options available out there. For completeness, I also want to mention the NI unit test framework. I've tried it, used it a bit, but I would be very hesitant to recommend it to anyone, to be honest. And then there's this one called InstaCoverage, which I haven't used myself, but for completeness, I wanted to include it here as well. And then we have my own favorite, which is then called LUnit, and I might be slightly biased, but this is the one that I prefer out of the bunch. And similar to VI tester, this LUnit tool follows the same XUnit pattern. And this pattern actually originates from, I think it's from Smalltalk, and it became popular through the JUnit framework, which is used in Java. But what it does, it defines some abstractions called a test class and a test suite. A test case is then kind of a container for all your tests. And a test is then a test method. And this would be a method which belongs to this specific class, which you then, so your specific test would derive from the test case class, and the method would then belong to that class. It also had this concept of setup and teardown. So we have a kind of a test harness, which is then methods in the test class called setup and teardown, and they are run before each test method. So the same setup and teardown methods are run before and after the test method, which you then define where you actually do the testing. And within the test method, you would use assertions. That's what it's called. These are basically functions which checks that what you get for result is what you expect. So you have some expected value, and from the code which you execute, you get an actual value, and you compare these to see that it actually does what you think it should do. And what the framework then is doing is running the setup method, running the test method, and running the teardown method, and then it's collecting results and visualizing that in some kind of way. But that's basically it. So let's have a look at LUnit. So as I said, I did like VI tester, and I don't think you should fix what is not broken. So I have actually used the same XUnit style as used by JKI VI tester and by many other tools out there. So I think this is an excellent way of organizing the tests, which works pretty well in my own workflow. So that's what it's based on. Then I had a set of design goals, which have emerged through the project. And yeah, here they are, all of them at once. But the first one is one that I'm gonna get back to in a bit. It's called, or it's about reducing the duplication of test code. And I'm gonna talk about this a bit later, so we'll get back to that one. I think, as I mentioned, when I run a test, I want to be able to tell immediately what has failed in the test. And I really wanted a quick and easy way to find out which test has failed, which test has passed, and that's obvious. But then I want to know, why did it fail? And I want to be able to locate that information very quickly. And that's something I'm going to show in a bit. I wanted the UI to be loading very quickly so that it's not disruptive. When you have a large test suite, the UI actually needs to find all the tests, and there's some optimization which has been done there to make sure that it's really quick and instantly just popping up, and you don't need to sit and wait for it to load and find the tests. The execution must be fast. The execution is in part depending on what the test actually does. If the test takes a lot of time to execute, then a quick framework won't really help you a lot. But I wanted it to be very fast so that the tests are run quickly, and it is actually much faster than anything else I have seen out there. I think that the workflow is very important, that it's intuitive and simple. So as you can see in the project, we have the test cases, and when they run, they get this small overlay indicating if they failed or if they errored out or if they passed. And then we can just run, run them or execute them in the UI using the right-click menu. And I wanted to have as well native CLI and CI support. So with that out of the way, let's have a quick look at what this actually looks like in practice. So let's see if I can get my desktop here. Is my desktop visible? It looks, yeah, I'm biased, that's true. So it looks like you can see my desktop now. So let's start by opening a blank project. So there we go. We have an empty LabVIEW project, and we can just go into Tools, and then we have the LUnit menu option here. And from here, we can just go on and create a new test case. If you used VI Tester, this is the same kind of workflow that you have there. For now, I'll just place it on my desktop. I'll not be changing the name. It's called My Test Case here. And I save it. And it should be added to my project here. There we go. And as of now, the test case doesn't have any test methods or VIs here. So we just have 2 templates. And to make this a bit more interesting, let's just create a test case. So we'll create it from this static test method template. So just right-click it, new from template, and there we go. So let's save this one. And now we have it in the test case here. You see that it's quite simple. This is just a template where you're supposed to implement something more interesting. This just checks this specific input. Is it a pass or not? And here we pass a false constant, so it should fail by all means. So let's just go ahead and run this one here. So we right-click it, we run it, and then we should get the UI open. There it's run, and it fails. We can click it here, and then we see, yeah, it failed. Now we don't get more details here than fail, and this is because we haven't added more detail to the test. So we can add a description here. Let's call it demo test. And we can add some more details. Hello, GLA Summit. So, and when we run it now here, we actually get the details here. So we can look at the test method by clicking at it. We see the details here and the description. So this is quite useful, actually. We have the test case here. We can see a summary of all the methods in the test case. And we can switch out the assertion to do something more interesting. We could just go into the palette here and use something like a pass if equal to make it more interesting. But let's postpone that for now. I also want to show the setup and teardown methods quickly. These should also be familiar from VI Tester. And we create them as we would with any dynamic dispatch method. We go into the VI for override on the test case class. Also, you might have noticed that this one got now a red overlay here because the test failed. Yeah, so let's create a VI from override for override, and let's create a setup method like so. And we actually have, it calls a parent, but this is just an empty method, so we can remove it. And if we want to do something interesting here before every test method, we could do it in this VI. If you want to pass data from this VI to this one, we would actually need to use the class private data. So we open up the control. We would add the data that we want to push the button. The data we want to communicate to the test method. We put in the private data like so. Then we can bundle it here. Let's just bundle by name. So create a constant. Let's put it to true. And then we can unbundle it here in our test method. And let's use that. This is a bit of a silly example, but I just want to show that the data is then communicated to this this test method. So if you go ahead and run this one here, run test case, you should see that we get it to pass because it feeds the boolean which we set in the setup method true, and we read it here and we assert that it is true, which we can see that it is. Oh yeah. Let's see. So yeah, you get the results here. You can save it to file if you want to. I have actually not come across a use case for that when you run it in the user interface. This is more for CI environments where you want to parse the results. But you can also pop out this result view, and this is quite handy when you run the tests and they fail and you work on them and you run them again and you want to have some kind of historic view of what did fail. Also, you still have all the information here about what did pass and the details. But apart from that, there's not really much to it. So let's just close this one down, and we can return to the presentation. Is there any? Sorry, I'm just gonna check the chat here before continuing. Yeah, I'll get back to Russell's question later. Karaya is a bit different, so that's more of a preference of workflow. You should add the question with QA. Yeah, I'm gonna check the chat later. Cool. So I'm actually gonna come to one of the features, which is why I felt like I needed a new tool in the first place. And this is because I tend to work with a lot of object-oriented LabVIEW, and when I want to test my classes, I have classes that might look something like this. We have the animal, a base class in this toy example. Then we have a few classes which inherit from the animal. We have a dog, a hippo, and then we have a child further down the hierarchy, which is called a hungry hippo. When I want to test this one, I tend to end up with something that looks like this. My test cases mirror the class hierarchy, and I have tests for all the different classes. Now, there might be some smart solution to this, but I hadn't found one. But now I have one, which I'm proposing here on how to solve this. So, sorry, I should maybe state the problem first. The problem that I was seeing is that when you work in this way, the animal class defines some kind of behavior. And if we then inherit from that class, we want to make sure that the dog and the hippo and the hungry hippo, all of them should adhere to the same behavior. They should fulfill the same contract that the animal class has set earlier. The way which I used to do this is to just copy the tests over. So it's not too much work to just copy over the methods, but it gets a bit tedious and it's quite error prone. And since it's manual, I would probably just skip it at some point, and then I would think that everything works as expected while it doesn't. It's also maintenance heavy. If I want to change the behavior of the animal class, I would go into every single inheriting class from it and change how its tests look like. So the way I wanted to implement this is to have a class hierarchy that looks like this. So we have the animal test, and this defines here 4 different methods. And the interesting thing here is that these are the dynamic dispatch methods. And the dog test only defines one test here. And in LUnit, we then slightly overload this idea of dynamic dispatching. So if a test case defines a dynamic dispatch, then it will be executed for all test cases inheriting from that as well. So we basically inherit the dynamic dispatch tests as well. So when we load this one in the user interface, it looks like this. So the animal test only has its own tests, and since these are dynamic, all the classes inheriting from the animal test class, they also inherit these tests. And I want to show what this looks like in practice. So let's open up this same toy example in LabVIEW. So here I have my classes. I have the animal classes, and I have the animal test classes. And here we can see on the animal class, we have the dynamic dispatch method, and we have the dog class, which only has this test for the dog. behavior then. So if we go into the tools, we open the UI, we see that we have all the tests here listed. We can run them, and they are all passing. And you can see that it works, or yeah, you can trust me that it works. You can't really see it. An interesting detail here is really, how does the dog test know that it should be testing a dog and not a generic animal when it runs the test case? And I've used a pattern here, which is basically during the setup of the test method. Let's open this one up. Here we do set the class under test. So we use the class is saved in this animal test private data. So they have the animal under test basically. And what we can do in the setup method of the inheriting class is to use this accessor to write to the private data. So this is nothing but an accessor. It writes it bundles it into the parent class private data. And when we then run the test here, then we of course need to extract from the private data like so. So when we run this for the animal class, we would have one setup method which first sets the animal under test to be like the parent base class here. We run the test, and then the animal will flow through this one, and these are dynamic dispatch methods, so they would, or if they are dynamic dispatch methods, then the correct method would be called. When we do it for the dog, then we would have the dog object or dog class coming here, and any dynamic dispatch would then be using the dog implementation. So in this way, we can define on the top level the behavior that we want to test, and then it will be inherited by all the classes that are inheriting from the top class by mirroring the test hierarchy there. There might be occasions where we don't want so these might be edge cases, because typically you would want everyone that's inheriting to be doing the exact same thing, but we might have something like a hungry hippo, and here on the animal class we had a test that an animal can't eat after eating because it's full, so it doesn't make sense to eat after eating. But a hungry hippo can eat as much as it likes. So here we would then need to change the behavior of the hungry hippo test in some kind of way, and we can just override this in the hungry hippo class, and in the VI then we can just skip it because a hungry hippo can always eat. So these are the kind of tricks you can use to build these kind of bigger test suites for classes then. Yeah, so as I mentioned, this was one of the things that I was feeling, that I was duplicating a lot of code, and I wanted to mitigate that in a way. And I was a bit frustrated with not being able to do this natively in any tool. So if anyone else has a good solution for this, I would be very interested in hearing about it. Maybe I can get some cool ideas for the future as well. Cool. I'm already a bit behind on time here, so let's just continue on. Yeah, there's been a lot of talk about continuous integration. Matthias Kubli had a great presentation this morning about the Jenkins, and I felt like releasing a unit test toolkit in 2020 should have native support for calling from the CLI and integrating with this kind of CI systems. And for those that are not familiar with setting up this kind of continuous integration service, basically you want to be able to call all your work to be done through the CLI. This is at least a very convenient way of doing it. So the CLI is command line interface. And then you want to be able to digest the results in some kind of way. And there's a kind of a standard way of doing this. So for LUnit, we can use the LabVIEW CLI, and I assume this would work very well in Matthias's tool as well, since he has support for all the LabVIEW CLI operations. So you can just then specify LUnit as the operation name, give it a path, and a path to save the results. And then we can set the number of test runners to run. I haven't talked about the test runners yet. I hope I have time for it. The results are saved in a JUnit compliant format, so we can just use the JUnit plugins directly, and it's digested by most CI tools out there. So yeah, as I already mentioned, it's quite important that this tool is snappy and that it doesn't stop you from doing your work. It doesn't break your workflow or is too disturbing to your workflow, let's say. As I mentioned, I think it's very important that the result interpretation time is quick. So I put some effort into making it as simple as possible. I think it works pretty well, but if you have ideas for improvements, just let me know. The UI load time, as I mentioned, it's important that it just snaps up and doesn't delay you for too long. At least when I work, I tend to just close it down a lot, and then I need to open it again. I close it down and open it, and I don't want that to take seconds. It should be sub-second. And then we have execution time, which is of course important, but it will also be depending on the actual tests that you run. So you have, as a developer, you have some responsibility to make your tests quick. So let's talk about what we can do to shorten the execution time. And LabVIEW is of course very good at parallelizing stuff. So what we can do is we can run our tests in parallel. And this is very beneficial if we have tests that look like this, where we have something that takes a lot of time to do. And we can just wait for that to complete. And if we run a bunch of these tests and measure the time it takes, now know that this is a log scale, a log scale. So what we see, there's a kind of perfect power law. So as you expect, if you double the amount of test runners, you would halve the test time because you would wait in parallel for all of them to complete. Of course, this is not probably a very realistic scenario, and typically your test code would be much faster than the 1 second delay here. And let's have a look at that. Let's first have a look at how we do it, of course. Yeah, so to configure parallel test runners, you just go into Tools, Configure Test Runners, and then you can set how many you want. Just be mindful that the code that you test must be safe to run in parallel so that it doesn't interfere when you run it in parallel. And what it does then is it schedules the test cases. It sends the test cases to the different test runners to be run in parallel. And you can see that it plateaus here in the graph. It goes down, and then it stops at 12. And the reason why it stops at 12 is because I actually have 12 test cases in this example. So adding more test runners doesn't really help because they just sit there idling. Let's have a look at a more interesting case where we have tests which are very quick to run. In this case, we have something like this. So basically, we just measure the overhead of the framework for running the tests because we don't do much more than make an assertion. And then we see that we don't have as drastic, of course, impact of parallelizing. It's still a factor of 2 or so. We can get it down to here using this, but we can't get an order of magnitude or so, which we could for the slow tests. This is a linear scale, so it's it's all very different from the other one. And final, so I already stated that that it's very fast than anything else that I've seen out there, and I feel like I need to show some kind of data to support this claim. I'm not showing this in a way to discourage you from using other frameworks. I'm not making any money out of this framework, so feel free to use whatever tool you like. But I think that I should at least show some data. Slight disclaimer, this is not a rigorous benchmark. It's just tests that I've done on 2 different computers to compare the different frameworks. And we can do something like this. In LUnit, we define a test case. We just make an assertion, and this measures the performance overhead of the framework. In VI Tester, we can do the same. It looks very similar, which is not by accident. And then we have Karaya, which I think would look like this if we do it. And if you look at the results, so what I've done is I run all the tests in the project, and there's a way for doing it with all these frameworks. And I basically clocked it on my phone to see how long it took. I had done a couple of iterations to take the average. And these are the test times that I got. So as you can see, the two left ones are LUnit. The leftmost is with 8 test runners in parallel. The second one is with only 1 test runner. The other two are for Karaya and VI Tester. If you don't believe me, the benchmarks are out there, so you can just go and run them yourselves. And if you get very different results, I'm very interested in knowing about it. I'm already over time, so let's just quickly go through this last slide. If you want to try this out yourself, you will need Lavi 2020 because it's developed using the community edition, so I haven't made it for older versions. It's available on GitHub, and as soon as I've figured out how to get it to VIPM, I will get it there as well. But there's a release on the GitHub page, which is a VIPM package, which you can just install, provided that you trust me. You'll get some examples, which you can have a look at. One is the same one that I showed you earlier. If you want to contribute, please share this with colleagues network, because as of now, we only have a user base of 1. So I'd like to grow that a bit to get more input and feedback. And if you have feedback, let me know. Use GitHub to report bugs, make feature requests. If you want to take an active role, just make a pull request or reach out to me directly. And you can find me on LinkedIn or on my mail here. So I'm sorry for the rush here in the last half of the presentation, but if you have any questions now, I think it would be a good time to go over these. There's a question if LUnit can be integrated with Jenkins, and yes, it can. You should look at the slide where I showed the CLI. There's also documentation. It's linked from the GitHub. Look at the documentation. There is actually a page describing how you would do that in general, and in Jenkins in particular, you basically call it to the command line interface, and you use the JUnit extension to digest the report which you get out of it. A lot of positive comments. Thanks for that, everyone. Oh, Q&A. Okay, where's that? There. Okay, what's the advantage of LUnit hierarchical approach vs storing a class in private data of a JKI class and populating a few instances of the same test class in a suite? I'm not sure I really follow. So Christian asked how he proposes a way of doing this in JKI Get Tester. I haven't actually figured out to do it in this specific way. I would say that the benefit of doing it in LUnit is that it's native. You don't need to set up a lot of scaffolding yourself. You can just define a dynamic test method, and then you would run the tests using the user interface, and it will run it for all the classes which inherit from the parent class then. You would need to use the pattern I showed to set up the class on the test. But yeah, I think it's pretty similar to what Christian is suggesting here, to using it in the class private data. I'm not sure how you would get that into the UI, but there might be a way which I'm not aware of. Eric Jens, so there's a difference, advantages between LUnit framework and VI Tester. I think the main ones are the work. So the main one that, for me at least, the main one is the workflow that you can that you get the overlays in the project. This is very nice for me personally, to be able to quickly see which tests fails and which passes. You have the option to run the test selectively from the project. So you right-click on the test case in the project and run it selectively. You don't need to run all of them. As I showed you, it's pretty fast. You can run the tests in parallel, and you have this way of testing classes using dynamic overrides. As Christian points out, there might be ways of solving this in VI Tester as well. So yeah, anyway, it's up to you. It's both tools are free and open source. So if you prefer VI Tester, I won't discourage you for using it. As I said myself, I do like it a lot myself. And then there's a question about testing code that interacts with hardware. And this is, of course, hardware and user interfaces are difficult. And I think that the way of doing it is probably to mock out the hardware and test the business logic, what your program actually does, and then have a mock for the hardware during testing. I wouldn't like to run unit tests with hardware anyway, because it would probably take a lot of time, I assume, and you would need to run them in the right environment and everything like that. So I think unit tests are not supposed to test the connection to the hardware specifically, I think. Let's see if there's any more questions in the chat before we can finish this off, and then we can move over to the last presentation here. Thanks for it, really interesting. All the best. Thanks. So far, I've developed it on my own, but if anyone wants to contribute, feel free. LUnit Low, all unit test classes are dynamically as scheduled using SGPI loads all, which can be heavy, thousands of unit tests. Yeah. Virtual. I'm not sure if I followed Tim's question. Not all the unit test classes dynamically or scheduled. So what's done? What it does is it creates basically a structure holding paths to all the classes or the methods. It doesn't load all the classes into memory, but if you have a new project, I would assume that they are in memory anyway. Tim, I need to get back to you on that one. I don't have an answer for you right now. Could you hit me up with a mail and we can have a discussion offline on that one? What about virtual instruments? Eric asks here. And I assume that you don't mean VIs, you mean something like a DAC-MX simulated channel. I guess that would work fine. Yeah, sure. You could do it. You would. One problem with that, or one caveat with that, is that you would have a global dependency, which is the DAC-MX simulated channel, which you would have to make sure that is available in any environment when you want to run this test, else it will fail. Even if the code works, the test will fail. Anyway, Eric, I think really the best way of testing or doing unit test is to have an abstraction layer for the hardware, and then you test that your code does the correct calls to the hardware. You can make mocks or a mock hardware class, which would then check what calls are made to the hardware, and you would check that it actually interfaces with the driver in the correct way. Then I would assume that the driver does what it says it does. I would not go so far as to test out the driver. That would be the responsibility of the provider of that specific driver, and I wouldn't write unit tests for it. Did that answer the question, or do you have follow-ups? Let's move this up here so that I don't need to put it down. Cool, yeah, but I think we should be heading back to the main stage to look at what's going on there. Thanks to everyone that have listened, and I'm very eager to hear what you think about this and getting some kind of feedback from actual users. So please try it out, and do not hesitate to contact me. And yeah, let's stay in touch. And again, if there's any Finns out there, get in touch. I'm very eager to get in touch with the Finnish LabVIEW community. That's all for me now, I think. Thank you very much.